This is This Week in Science and Education, episode 21, Buckyballs.
With a B.
Always giving me stuff to...
And so it begins.
This Week in Science and Education, brought to you by Mueller Systems. Need a backup? Check out MuellerData.com/VROT. That's MuellerData.com/VROT. Hey everybody, it's time for This Week in Science and Education. This is your host, Kevin Cougler, the show that talks about all things related to science discovery and health research, and we're taking that information and we're making it available to teachers to use in the classroom. Well, thank you for joining us here today, and as always, with me from the Kawartha Pine Ridge District School Board is my friend Colin Jagoe. How you doing, Colin?
I'm just dandy, my friend. How are you today? It's been a long time. It's been a couple of weeks since we've sat face to face. I hope everybody had a good holiday.
I didn't have a good holiday. I had to do 2 shows without you guys while you were gone having fun.
They looked fabulous, by the way. Thank you for all your efforts. We really appreciate it. You get a raise. You'll get a raise from now
on. That's a shameless plug, but I love it. Laurentian University, Thomas Merritt is up there. How are you, Thomas? Did you have a good vacation?
I'm very well. Had a very good vacation. I've got 3 graduate students that are trying to defend, so I didn't have much of a vacation, but what vacation I took was very nice.
Excellent.
Well, I have to admit, whenever I was on the site, I looked and there was at least one user that was logged in, and often it was you, so I know that you were thinking about T-WiSE while you were on vacation.
If you say so.
Guys, I'm going to introduce our guest here today. We're pretty privileged to have Dr. Jan Cami. I'm going to read a little introduction for him, and then Jan, I'll ask you to introduce yourself, of course, and talk about your research. So, Dr. Jan Cami is originally from Belgium, where he obtained a master's in physics at the University of Leuven. Did I pronounce that right?
Leuven, that's quite close, yeah.
Leuven, okay. Well, we're getting there. In 1995, under supervision of Professor Christoffel Watkins. He then moved to the University of Porto, which is in Portugal, and then to the University of Leiden.
Leiden, yeah.
Okay, all right. To obtain a European Master's in Astronomy and Astrophysics in 1996. Dr. Cami obtained his PhD in Astronomy at the University of Amsterdam. See, I got that one. That was no problem. In 2002, and his PhD thesis was titled Molecular Gas and Dust Around Evolved Stars. The fellowship of the NRC, the National Research Council, brought him to NASA Ames Research Center in California in 2002 to work first with Dr. Farid Salama and later Dr. Louis Alamendola on the topic of large complex molecules in space. He subsequently became a research scientist at the SETI Institute in Mountain View, California in 2005, a position which he still holds part-time to this day. Cool. Since 2006, he's been an assistant professor at the University of Western Ontario in the Department of Physics and Astronomy. Dr. Cami's research focuses on astrophysical applications of molecular spectroscopy, astromineralogy, and the study of circumstellar environments of evolved stars and the interstellar medium. So I guess we can get started. You can correct me on all the mispronunciations we had, but thank you very much for being here today, and feel free to tell us a little bit about your research.
It's my pleasure to be here. Actually, that was pretty well. Most often I hear all sorts of pronunciations where I don't even know that it's about me, so that's quite good. And I think you've already said most of what I've done in the last 15 years. I've primarily been studying molecules, so chemical substances of all sorts of sizes, types, complexities in space. The way we do that is with what's called spectroscopy. We detect starlight, or sometimes we see how starlight gets absorbed by chemicals as the light travels towards the Earth. We send that light through a prism that breaks it up in different colors. And often there's a pattern of dark lines superposed on that typical rainbow pattern that you see. And that really is fingerprints of molecules and atoms. And so ever since I did my master's thesis, I've been very interested in seeing how we can use that, not necessarily just to fingerprint chemicals and say, yep, those are there, those are not there, but to actually use them as thermometers or to measure things like densities or the amount of radiation in a certain place in space. And so I've been doing that sort of work for about 15 years. And of particular interest, and I guess it's the main reason why I'm here right now, I've always had some interest in large molecules. I remember when I was a teenager in 1985, chemists discovered this totally new form of carbon molecules, which were shaped like a soccer ball. As a European, I always tend to say football, so correct me if I do, but really it's in North America, it's a soccer ball. And I found it absolutely amazing, especially when I read the reports on how these chemists, they couldn't see these structures, but by just carefully studying the results of their experiments, they could figure out the whole structure of this molecule. And I found that so cool, and then when I did my master's thesis, at some point I was studying some of these absorption lines, when somebody suggested, well, maybe it is these soccer ball shaped species, which at that time they certainly were not, but kind of kept it in the back of my head. And then last year I just happened to stumble really over an observation done by the Spitzer Space Telescope, which showed exactly the fingerprints that I had been expecting for these molecules. And so this is something that people have been looking for 20 or 25 years. In the meantime, after our discovery, many more people saw these fingerprints of these species in their observations. So we now see that really those buckyballs, they are everywhere. That's typically about 1% of all the carbon is locked up in these balls.
Now, actually, if I can interject, you used the term buckyballs.
Yes.
Can you tell the folks at home a little bit about where that comes from?
Yes, it's a very interesting story, and there's a very funny ending paragraph in this scientific paper that describes the discovery in 1985. It's also the only paper, I think, that was ever published in the journal Nature that has an image of an actual soccer ball. And really what it is named after is it resembles a geodesic structure that was popularized by the architect and futurist and inventor Buckminster Fuller. He had a weird first name, but he was well known to the chemists that discovered these buckyballs. And so as some sort of an honorary attribution, they named the molecule with 60 carbon atoms that is shaped like this soccer ball, they named it in full Buckminster Fullerene. And actually in the last paragraph of their paper, they say that they are a little bit disturbed by the number of syllables in this term, and they suggest some alternatives like balline or what I like more, carbo-soccer. But in the end, by consensus, the Buckminster Fullerene kind of stuck. Most people will now call fullerenes the entire class of these molecules that are shaped like a ball or an ellipsoid. And so in short, since Buckminster Fuller was known by friends and enemies as Bucky, they're called buckyballs.
I think that's a great story. I'm not aware of too many scientific discoveries that are actually named for people other than scientists or researchers that found them in the first place. So,
we have a sense of humor. It comes up every now and then. It's not common. But if you look at
your sense of humor, I had to edit that entire Science North video thanks to you last week.
Yeah, I bet you did. In genetics, there are a lot of genes that are named after some sort of semi-humorous spin on whatever it was that you found. Jan, I appreciate the football soccer ball. I can remember when buckyballs were described in the mid-'80s, and I was reading one of the papers this morning, and it said something about these football-shaped molecules, and I'm like, really? I thought they were shaped like a soccer ball. I've lived in England, and I forgot that we were on the wrong side of the pond. So, yeah, they are often described as football-shaped. You just have to make sure which continent you're talking from.
That's right. That's right. Can I ask a question?
Sure.
you made an interesting comment, and I want to ask you about it. You said something to the effect of, I stumbled across the spectroscopic signature by accident. Could you explain what you meant by stumbled across it by accident? Because I have a feeling it wasn't exactly an accident. Talk about maybe the discovery and how that actually occurred.
And we are streaming live on the internet, by the way.
Yeah. Well, well, okay. Maybe it's not entirely an accident, but
Chance favors the prepared mind, right?
It's not that we carefully planned for this discovery at this particular time using these observations. I was well aware of the spectroscopic side of Buckyball, so I would certainly recognize the signatures when I would see them. And I knew that several people or several teams had been looking for them. They had been suggested already as being present in space, but there had so far not been very clear observations that really unambiguously showed that this really are these buckyballs. There's lots of confusion. There's many other species that contribute that have their fingerprints that basically make the observations kind of dirty. And so within this whole forest of fingerprints, to identify like a few very specific lines is very difficult.
Sure.
And then in February, what really happened is that one of my friends and colleagues, Geronimo Bernard Salas, who I know well from my time as a grad student in the Netherlands, he's an expert on planetary nebulae, and that are objects, all stars that ejected their outermost envelopes. And in his search for analyzing observations made with the Spitzer Space Telescope, which was until recently the only infrared space observatory we had available. It's dead now. It's not operational anymore. And so he collected all the observations of planetary nebulae. And since he's one of the world's experts, he's seen pretty much all infrared observations of that sort of objects. And he came across one specific object where he looked at the observations and he had no idea what he was looking at. He recognized immediately that it was a very clear signature of something, but he wasn't quite sure what it was.
Right.
And sure enough, he clearly assumed it would be a carbonaceous type molecule. It's an environment which is very rich in carbon typically. And what happened is that he actually asked my girlfriend, who's also a professor here in astronomy, who's an expert on a different class of molecules, polycyclic aromatic hydrocarbons. Those are large, kind of planar, flat carbonaceous molecules. The reason why he asked her is that in the past, some of these fingerprints had been suggested to possibly be due to that sort of polycyclic aromatic hydrocarbons, and since she's one of the world's experts, it was an obvious choice to ask her, and she looked at it and she said, no, I have never ever seen something like this before. And then she asked me whether I had any idea what it might be, and since I was well aware of previous searches, I immediately recognized the fingerprints. And so in that sense, that the spectrum or the observations happened to land on my plate at that time, that I think was coincidence. I'm also fortunate that before moving to Western, I worked at NASA Ames astrochemistry lab, so I had a very good feeling for the chemistry literature, which I needed to finally prove that indeed what we were seeing were the fingerprints of these buckyballs. So.
Right.
I guess it's a case of where luck favors the prepared mind.
Exactly. I was going to say, there's not a lot of chance involved there when you're really good at something and people find you for that reason. That's not what I would call luck, but no, that's a great story. It's really neat to hear that the observation was pulled out of another observation that somebody was doing for another reason. And I've often spoke to students and said that some of the greatest discoveries are made when people go, huh, that's weird. Because they don't know what they're looking at, and then they have to dig into it. So that's an example of that story. That's really cool.
Yeah.
Dr. Cami, talk a little bit, I'm just thinking, I'm grade 9, grade 10 science students, break it down a little bit, the importance of the discovery and what this means. Can you relate it in terms of the everyday person to?
Well, yeah. In the first place, I think there's a really high coolness factor, and whether you're a grade 9 student or you're a researcher, I mean that kind of coolness factor. there.
That's
Yeah,
very. Do they still stay
Don't-
cool though in grade 9? Colin,
Yeah,
or do
they
say
do
no?
actually, or maybe it's mostly me. But
Okay.
it's said. I'm not sure who says it, but it's definitely said.
Yeah, yeah.
All the teachers say it.
Yeah, at some point. But anyway, so that factor is still there, and I think for myself that is maybe one of the most rewarding elements of it. In terms of science, well, when these molecules were discovered in the lab, it was found that these are extremely stable. It's very hard to kind of break them apart, and so it was immediately suggested that they would be ideal candidates to survive in deep space, because deep space is not your everyday holiday type of destination. It's a low density. There's a very strong radiation. There's pretty much everything is trying to destroy you there. So you need to be a strong molecule with a well-built skeleton to really survive there. And so these Buckyballs really fit that bill. And I guess scientists, they like to be right. I mean, this was suggested 25 years ago, and in the discovery paper in '85, people have been looking for them and didn't find them. And so it's very surprising if you have something which is very stable, which in these laboratory experiments you form relatively simply. I mean, you don't have to do very artificial things with your laboratory setup. So it's puzzling that they were not found before, and so now finally we find them roughly in the place where we expected them, around a dying star, which is carbon rich. There's a whole series of other questions that are raised now that we don't fully understand. But so finally our idea of that these complex molecules self-assemble if the conditions are right, that's a good confirmation of that. And what I personally find intriguing is if you step away from it all, it's kind of easy to imagine that a chemist in a lab could carefully assemble carbon atoms together until you form the shape of a soccer ball, which is pentagons and hexagons alternating in such a way that you have the 60 carbon atoms making a soccer ball structure. And that's kind of easy to see that a chemist could do that in a lab. But here we see Mother Nature doing exactly the same thing without any outside help. It's just a matter of creating the right conditions with the right ingredients, and spontaneously these complex three-dimensional structures, they self-assemble. And so for me, that actually is intriguing, because now I start wondering, how complex can Mother Nature build things in space without any help whatsoever. So it opens up an entire field of complex chemistry. The Buckyballs themselves will have a role in that. For instance, it is found from laboratory experiments that you can on the outside surface you can grow other small molecules which you would otherwise not be able to grow in space. So they might play a role in there. And it's about 1% of the carbon which is locked up in these Buckyballs. There's all sorts of other possible applications. These Buckyballs, they can be used as a cage. I find that a very intriguing idea. You can lock up atoms or small molecules inside this cage, and then they cannot escape. And recently, actually, chemists have made what they call a Bucky bottle. So with the right chemicals, the top part opens up, then they can put in a water molecule and then close the Buckyball again. I find that intriguing, because who knows, maybe within these Buckyballs some atoms or small molecules are locked up and transported over astronomical distances and possibly be incorporated into solar system, planets, who knows?
Hopefully that doesn't mean that everything that comes out of this is going to be named Bucky something or other after.
No, I can assure you that right now I'm a bit tired of saying the word Bucky.
Let me ask a question. Jan, if you could just maybe back up a little bit. When teachers are talking to their students about these results, and they're going to talk about the spectra that you found and the fingerprint in that spectra, can you tell us a little bit more in terms that we could get across to a 9th, 10th, or 11th grader? What are the spectra? How are you actually generating this data that you're using to make your discoveries, or that somebody generated it for you to make the discoveries?
Okay, that's a very good question, actually. There's two components that are of importance. One is the laboratory component, and the other is say, the space telescope that we need to do our observations. The fundamental principle is that at a small scale, atoms and molecules, they interact with light in a few different ways. Molecules particularly, they vibrate in all sorts of different ways. These buckyballs, they jiggle a bit like jelly, you could say. And these vibrations, they allow them to interact with light, but only on very specific colors of light. And for molecules, that is typically at infrared wavelengths. So the way we identify these species, simply put, is I looked at laboratory experiments where they measure the colors of light that these buckyballs emit when they vibrate. And that results in a sort of a fingerprint in a spectrum. And then I compared that to an astronomical observations where a space telescope looks at a very specific objects that also generates a fingerprint if these molecules are there. And basically by putting them side to side, you can see whether there is a match or not.
So you're working. I'm sorry. In that case, you're working from a standard to your observations. Can you work the other way? If you have a fingerprint that you don't have a standard for, can that fingerprint suggest the kind of molecule that it would be and that you could go out and try to do either construct or find the correct standard for?
In many cases, that is actually the case. But it really depends on the specific circumstances and the specific molecules that you're looking at, and also a little bit on the wavelength of light that you're studying. At infrared wavelengths, often if you look at simple molecules, there's more information in the precise shape of the absorption lines that you see, and that allows you to determine things like the size and the geometry of your molecule. In other cases, it's much more difficult, and one very known problem in astronomical spectroscopy is called the diffuse interstellar bands. That's a series of 600 of these absorption lines at optical wavelengths, and none of those have been identified. And the only way to kind of get some idea of what molecule might be causing those absorptions is to really study the precise properties of the absorption lines. And indeed, if you look in different lines of sight where you see that the conditions might be slightly different, for instance, you have a lower temperature, you see that the band becomes a bit narrower from measuring those changes, you can get some idea again of the size of the molecule. And that tells you something about the nature of the carrier. But then ultimately, really, I think the community only accepts an identification if you have a perfect match between astronomical observations and a laboratory obtained spectrum.
That's awesome. Thank you.
Dr. Cami, and I guess, Colin, this question might be for you as well. I'm just wondering if we can put an educational spin on this. Like Marissa Cooper from our office today dropped some Buckyballs on my desk. And it's this little thing about like this.
I'm assuming they were models. I'm assuming they were models.
Yes, models, not the actual balls. Right. Thank you for clarifying. Yes,
that's okay.
She reached
that's what I do.
Space and grabbed them, and so I'm holding these things and I'm thinking, geez, I hope this isn't like the Rubik's Cube because I still haven't solved that, and that was out 30 years ago. But what can students be playing with in the classroom to help them learn a little bit about this?
I actually had a bit of a question around that this sort of fits into, and it actually had to do with the structure of the Buckyball itself, right? And this sort of plays into how students can learn about this. The 60 carbon shape. Is there something fundamental about carbon itself that sort of leads to that self-assembly in that specific shape? Like, we think about how ice crystals form due to the molecular bonds in water, right? And how those crystals are a direct relationship to the properties of the water. Is the Buckyball a direct derivative of the properties of carbon?
That's a very good question, and I think the honest, truthful answer is that we're not entirely sure. After many years of research, we're actually not entirely sure exactly how these Buckyballs self-assemble. There was a paper last year where they start from a graphene sheet, and so graphene is something like chicken wire on say microscopic scale made of carbon. And what they managed to do is somehow they knock off one carbon at the edge. Then instead of having a 6th ring, that turns into a 5 ring, and then the whole thing kind of rolls up on a short time scale. What I find interesting to do with these models, and of course I ordered some of these models myself and started playing with it, is the question why do they curve up? And so carbon is a very interesting sort of element because it can form 4 bonds, and one of the types of molecules that forms are called aromatic species, where the carbon molecules assemble in a benzene ring. So it's 6 carbon atoms in a row, and they kind of share all the electrons, and that's a very strong type of bond. And so an entire class of molecules, these I've mentioned those before, the polycyclic aromatic hydrocarbons, they are just one of these, a whole series of these benzene rings right next to each other, and so that looks really like chicken wire. Now, interestingly enough, if you take one of these models and you try to build something which has one of these benzene rings in the center, and then you just build 6 rings around them, it's perfectly flat. It's a totally flat type molecule. If you try to do the same starting from a central 5 ring, from a pentagon, there's no way that you can keep it flat. It kind of curls up. And so it is the presence of this 5 ring in the structure that makes the whole thing curve. And so the result of that sort of molecule would be a kind of a bowl-shaped species.
Right.
And so the interesting thing about C60, and which it's also the reason why it's the most stable one, it's the smallest configuration where you can completely close this cage without having 2 of these pentagons touching each other.
Right. Right.
Slightly larger version is C70. We also found C70 in space, and it's a bit elongated. That looks more like football. Okay.
Cool. So if Kevin starts to play with his models, could he replicate that sort of self-assembly thing? If he took it all apart and then tried to piece it all back together, would it, by its nature, form that ball?
Well, so if you build in a 5 ring, then it starts curling up. But then the precise reason, I mean, what must happen in such a case is that you break more bonds, you turn more of these 6 rings into 5 rings, and exactly why that happens is not quite well known.
Sure.
All times, what people used to do all times, what people used to do to make these bugs is they would
in the 90s.
Yeah, exactly. That's like so 21st century. What was I say? Oh yeah. So what they used to do is actually put an iron on top of a flat layer of carbon, and now the iron would basically cause the whole thing to roll up. We actually managed to make kind of a movie of this. So researchers have managed to kind of film the individual steps of how that process happens. So we're at the stage where we kind of see how it happens, but it's not entirely clear yet why or exactly how it's happening. So.
Right.
Go ahead, Thomas. I think you wanted to jump in there a little while back.
Well, just when we were talking about the 5-member rings, doesn't this tie back to the source of the names? I mean, wasn't that Buckminster Fuller's geodesic domes? Weren't those components of his domes pentagons? And that's what gave the stability and strength to those domes? Or am I making that up?
He made a whole series of different domes, and actually he started off, and it's an interesting story too there because as a child he had problems in school with geometry. I find it a fascinating story. If a teacher would draw like an X on the blackboard to represent something going into the board, he could not imagine that. So what he needed to do is he needed to go home and kind of make models of these geometric shapes to really have a look at how these things work. And so his first experiments or the first series of geodesic domes that he was making did not use pentagons or hexagons at all, but they used tetraheders most of the time. And then he gradually moved onto hexagons and pentagons, and I think indeed he was one of the first to realize that you need these 5 rings in there to close the entire dome, and at the same time, if you do that closure, that alternating of 6 rings and 5 rings makes it completely self-supporting. So you can build a ball like this, and you don't need any support structures to support. Yeah.
Colin, how long before some of this research makes its way into the classroom?
It's there now. right? Kids are playing with models as we speak. So, and I mean, the Buckyball shape is so interesting that, and it's so engaging just to realize that this can happen. I mean, it's there now. When you talk about why, particularly in chemistry classes, why molecules actually are shaped the way they are. They're not just formulas on a board. They're three-dimensional objects. So we're doing it now. There's, so it's there. And the fact that we're now finding these things in space, like you said, that's just engaging in and of itself. But it's one more level of hooking kids into realizing that you can do really neat things in science. And more interesting, it's simple to understand, but there's really cool things yet to discover, right? Which is really, really neat.
Well, maybe we can point the kids to your website or to some websites that you know of where they can find out some more information about your research. David, can you tell us where to go? Or
Well, yeah, I have a website at the university here, the University of Western Ontario. Unfortunately, it's not very current, I must say. What might be interesting there are a couple of YouTube videos. In particular, one was made by NASA. So if you search on space soccer balls, I believe, you'll find it as something that kind of shows also how these buckyballs vibrate and how that interacts with light. And, so I find those very, very instructive.
So we'll find those links and we'll put them up for our audience in the show notes area. It's vrock.ca or at the new vrock.wordpress.com. We have our show up there as well. Search for This Week in Science and Education. Dr. Cami, thank you very much for coming on the show today. We appreciate your time and hearing about your research. We're going to break now for a little bit of a message from our sponsor, but would you be so kind as to stay for our news item?
Sure, absolutely.
Thank you very much. So I'd like to talk a little bit about Mueller Systems. They are the company out of Woodstock, Ontario that is really your #1 resource in terms of having an effective backup for your home computer or your work computer or your network. The backup software and expertise provided by Mueller's protects your data and saves those all-important pictures of the grandkids or those files that you're working on at the last minute at 2 o'clock in the morning for your director of the school board like Colin Jagoe does. And you don't want your computer to go down and crash because then you got to come in at 4 a.m., right, Colin? So we encourage you to get your computer backed up, and to find out some information on that, go to muellerdata.com/vrock. That's muellerdata.com/VROC. If you go there today, you can try out the backup software for 90 days, absolutely free of charge, and they will even call you and help you configure it and set it up. That's how good these guys are. So we really encourage you to do so, and we thank Mueller Systems for their support. Gentlemen, we have a news item today. Who wants to talk about this chemistry, trials of new carbon? Was that you, Jagoe? Who was that?
We lost him.
We lost him.
Sorry about that. I got the wrong button. I pushed the wrong button. I apologize. I
don't want to talk about it. Just say so. We won't take it personally. It's okay.
No, I couldn't remember if it was me that sent it out or if it was somebody. It doesn't matter. It was actually just an interesting article that seemed to tie into the Buckyball story that we were talking about, because basically the article talks about all of these sort of new forms, quote unquote, new forms of carbon that we're finding. Buckyballs being one example, but then the newest graphene, and in between them carbon nanotubes and things of that nature. And the article sort of talks about the potential that these things have been said to have had for 20 years now, and that it's still not paid off really in any big way for any of them, and saying that maybe graphene is sort of the new one, and it seems to maybe have a few more applications that might be actually practical, as opposed to things like carbon nanotubules that we've been hearing about for quite a while, but really haven't found any mainstream applications. So that's sort of the gist of the article, and there were some interesting things in there, and I thought it might be worth talking about today.
One of the things that I thought was interesting, Colin, I don't have the article in front of me, sorry. When do you remember when it came out? What was the release date on that?
January 6th, 2011.
Yeah, so we actually talked about this last fall the cover of Nature, so the article that you sent us was from the journal Nature. The cover of Nature from somewhere in September, October, was this story about graphene was going to revolutionize the way that we sequence DNA. And I had assigned the course that I was teaching in bioinformatics, I assigned them the op-ed piece and the science note in that issue to read, because we were talking about how you sequence DNA. And the whole point of the article was to say, yeah, we can't do this. And it's the cover of Nature saying that graphene is going to revolutionize the way that we're going to sequence strands of DNA. And then the article says, perhaps in 10 or 15 years, we'll be able to use this or similar technology to sequence DNA. But that's not what the cover said. The cover said, you know, we are there, and this is amazing. We've revolutionized science as you know it. And here's an article in that same journal from a couple of months later saying there's been so much hype that these carbon molecules are going to revolutionize science as we know it, and none of that's been realized yet. And I really was waiting for him to cite Nature in the article in Nature saying, and Nature is one of the worst offenders in this case for having done this.
But they do say that graphene is in this article, it says graphene has the best potential. Right, so he's sort of supporting what. It's interesting, isn't it?
But at least he's saying potential. I read the first few lines of that article, and I was thinking, you know, your own journal is doing exactly what you're saying, that they're hyping up these molecules. But then the rest of the article makes it very clear that the whole point is that there has been too much hype, that there is a reality to the molecules, and there are potentials there. But it was interesting to see that. One of the things, Jan, when you were talking about the self-assembly of the Buckyballs in space, with the kind of information that you get, do you get an idea on how uniform the size or shape of these balls are? You know, that's one of the issues, I guess, especially with the nanotubes, that they're not uniform enough for industrial, practical applications. So how uniform are Buckyballs that are forming de novo in space?
Well, we can measure that quite accurately. The ones that we see are exactly the 60 carbon and the 70 carbon fullerene species, and we haven't found anything else yet. There's still some room in the spectra for some related components, but there's no other components that we have seen. And the 60 carbon atom version we see everywhere. Now of course what we see is a whole assembly of very small individual molecules that we see emitting light. That's very different from getting something like a carbon nanotube that you have to grow to a macroscopic size to actually be useful, right? So it's the difference in scale of yeah.
That's great, thank you.
Anything else you wanted to add on that, Colin? Or
well,
should
I
we
mean,
switch to,
no, that's fine. Some of the. There's been so much hype over things like nanotubules and that sort of thing. Where do you see this whole field going, like in terms of practical applications? Because that's, you know what, as much as we sometimes don't like to think about it, because science itself is interesting, when you're talking to kids and public, sometimes they want to know, okay, so what? What do we do with it? Like you mentioned the Bucky bottles and potential of putting other molecules inside the Buckyballs and nanotubes have the potential for like material sciences and sort of graphene and that sort of thing in electronics. What do you see maybe some potential practical applications of some of these things off in the maybe not too distant future?
Well, I think there's, well, it's a bit a dangerous word. I mean, there's lots of potential applications, right?
There you go.
That need to be tested, but it's not easy science necessarily. For instance, if you think about the Bucky bottle concept, clearly, if you would be able to lock up specific drugs in this Buckyball, transport it in a human body, and open the bottle exactly when you need to, that would be much more efficient drug delivery. Whether or not that is something that can be done, that takes a long time to research. The same thing for carbon nanotubes and for graphene. If you can make sure that the whole process that leads to the creating them in bulk properties of sufficient quality, then the applications are endless. And I think that's what the industry is somewhat betting on. Even if it takes a long time to get to that point, then the payoff will be huge. You'll have very strong and lightweight materials. That's the whole lure of these materials. They're very light for the sort of strength they have. So so that's, I think it's worth to at least investigate to the end whether or not you can possibly tap into that potential.
Right.
Yeah, I think that's a really good point. And whether or not the next generation of electronics are built on a carbon-based system, the one thing that we can be certain of is that electronics will change through time.
Mm-hmm.
And if nothing else, when you're teaching students about these kind of concepts, you would be remiss in saying, right now we are doing this and we will always do this. We know that things will change. And I think the article that you sent us made a really good point about the amount of time that's gone into silica-based systems versus where we are now on the carbon research, that we just haven't had the time in there. I don't think the author is saying that necessarily carbon-based systems are what is coming next, but something else will be coming, whether it's just an evolution of the systems that we have now or whether it's a radical departure. And I think you can get that point across to students. And you can balance it by saying just because it is the next hip thing doesn't mean that it will be the next real thing. But change will happen. And it's a matter of teaching students the balance between those. And the excitement factor is a big deal. Getting students excited about the potential to develop new materials, new technologies, new advances, that's great. I thought one thing that was particularly neat in that article, you've got it hopefully in front of you, the weight of the fabric that would be necessary to hold a cat.
Yes,
so
I saw that.
You would be slinging a cat, and they've got a weight on the cat, about 14 pounds.
They said about 4 kilograms, I think, is what comes to mind.
4 kilos?
Yeah.
For a 4 kilo cat with a 1 meter, you have it there, Kevin, with a 1 meter square fabric that weighs less than a whisker.
Now, admittedly, a 4 kilogram cat's not a big cat. I can tell you from my cat at home that is nothing in the cat world. But nonetheless, you are lifting that cat with a whisker. And that definitely falls in the holy crap, that's cool category. I mean,
0.77 milligrams.
0.7.
That reminds me of... Go ahead, Thomas.
Just to put that in context, one of my flies weighs approximately 0.7 milligrams.
There you go.
So it's the weight of a cat's whisker or the weight of a single Drosophila melanogaster.
Yeah.
And this is a 1 meter sheet of fabric, a potential 1 meter or 1 meter square potential fabric. So how cool is that?
That is awesome.
That's amazing. One of the things that I heard today is, we're just at the start of some of these discoveries, and if you're some kids out there and you're looking for possible career choices, it sounds like there's going to be all sorts of new areas that they can enter into for these types of this type of research.
Lots of research.
So, gentlemen, I think it's time to wrap up for today. I'll give you guys a chance at a last word. Who'd like to go first? Nobody wants to go first. Tom, I'm picking you. You're on.
I think we're done. That was awesome, Jan. Thank you again for coming in and talking to us. I really appreciate it. And honestly, your description there of how the data that you're working with is generated, how that's analyzed, helped me immensely. It really puts that in a better perspective for me. Thank you very much for that.
Yeah, absolutely. And I mean, Buckyballs is such a neat concept, and the fact that we finally found them in space for the first time, and the fact that it was a Canadian who did it is just so cool. And I just want to thank you for your time, and thanks for the research, because it's really, really exciting to know that people are out there doing that sort of stuff.
Thank you very much. My pleasure.
Okay, thanks, guys. And just on a personal note, welcome back. Really missed you guys while you were
Happy New
gone.
Year.
This is way too long. Happy New Year to you. And just interestingly enough, I shouldn't give the impression that these guys weren't working. Colin, for instance, over the holiday, called me from some obscure cabin out in the middle of, I don't know where he was in New Brunswick, but...
middle of the woods in New Brunswick.
Yeah, what? Tell the folks what we were doing there, because
it's a video conferencing thing, right? And Skype just released a new app for their iPhone, and you can do video conferencing through your iPhone, through Skype, on a 3G network. So I was at my stepdad's at a cabin in the woods, kilometers away from any Wi-Fi zone, and I called Kevin and showed him where I was, and we had a little chat via Skype video over the holidays. So, just new technology, pushing the limits of what you can do, and of course we have to dive in and play with it and see what we can do with it as well. So it was a lot of fun.
Absolutely. I love that about you, man. That's awesome. And I also love the fact that you can't live without me even when you're on vacation. You know,
You're the only guy I knew I could call who'd be excited about it.
You guys need to get out more.
I was in the woods. I was out.
You were in the woods attached to your cell phone. That should tell you something. Gentlemen, thank you very much. I'll see you next week.
Take care,
Thanks
buddy.
a lot, fellas. And on behalf of Thomas, Merritt, and Colin, Jagoe, that's another episode this week in Science and Education. We'll see you again next week. And thank you very much, Dr. Cami, once again.
My pleasure.
Take care,
Really,
everybody.
thank you very much. That was awesome.
Thanks.